Let's perform a brief count of the leaves of this plant in the pot. Let's continue counting until we encounter another leaf on the same level. At this point, let us also remember the number of turns we made around the stem. The two numbers we obtained, the number of leaves and revolutions, will be the first two numbers we see in the Fibonacci series. Had we begun counting in the opposite direction, then we would have obtained the same number of leaves, but at a different number of revolutions. The number of turns in each direction and the number of leaves encountered during these reveal three consecutive Fibonacci numbers. These sequential forms may be circular or spiral, depending on the species of plant. One of the most important results of this special sequencing is that leaves are arranged so as not to cast shadows over one another. According to these proportions, known as leaf divergence in botany, the order in the way leaves are arranged around the stem has been determined with particular numbers. This arrangement is based on an exceedingly complex calculation. If n is the number of revolutions we need to make, beginning at one leaf, until we encounter another leaf at the same level, and if p is the number of leaves encountered during this cycle, then p divided by n fraction is the leaf divergence that exists in plants. Leaf divergence equals number of leaves in a leaf cycle divided by the number of revolutions. Fractions peculiar to some plants are as follows: 1/2 in meadow plants, grasses, 1/3 in marsh plants, 2/5 in fruit trees, apple trees for example, 3/8 in banana species, 5/13 in bulbous plants. The way that every tree from the same species is aware of this ratio and abides by the proportion determined for it is a great miracle. How does a banana tree, for example, know about this fraction, and how, no matter where it may be in the world, is it able to abide by it? According to this calculation, when you begin from any leaf and make 8 revolutions around any banana tree trunk, you will encounter another leaf at the same level and at the same time encounter 3 leaves in this cycle. No matter where you go in the world, from South Africa to Latin America, this fraction never changes. Just the existence of such a leaf sequence ratio is important evidence that living things cannot come into existence by chance, but that they were created with an exceedingly complex structure. It is Almighty and Omniscient God who encodes such a proportion in the genetic structure of living things and creates them with that information. The numerical miracles we encounter in plants go further than these. Although the branches we see on the trees around us may appear to be arranged haphazardly at first glance, they, too, are actually arranged according to an exceptionally complex plan and mathematical calculation. Botanists have identified the golden ratio numbers inherent in the branching of a growing plant. We may now consider the example of the sneezewort plant. Let us look at the relationship between branching and the golden proportion in this plant. As the plant grows, a new branch emerges from every bud, and a new branch from that one. If the number of branches in a horizontal plane is counted, then Fibonacci numbers can be seen. The Fibonacci series is an important key to understanding the fine calculation and arrangement in plants. This shows the order and aesthetics in leaves and flowers arranged according to the Fibonacci series. The fact that plants are shaped according to specific mathematical formulae is one of the most evident proofs that they have been specially created. The sensitive measures and balance in plant atoms and DNA also exist in the plant's external appearance. Other proofs of creation involving the golden ratio include some flowers, seeds, and fruits. The sunflower is one of the finest examples on this subject. If you pick up and examine a sunflower, you will see that its seeds are arranged in spirals. And if you start to count all the seeds in the spirals turning to right and left, you will find 2 consecutive numbers from the Fibonacci series. This is certainly not limited to the sunflower alone. The leaves of densely seeded plants, such as the cabbage, also form spirals running to right or left around a central point, as in the sunflower. Daisies and pinecone scales are also set out in right and left spirals. If you count these one by one, you will again obtain numbers based on the Fibonacci series, in other words, on the golden ratio. These numbers in the spirals in plants will be 5/8 and 8/13 in pine cones, 8/13 in pineapples, 21/34 in the central florets of the daisy, 21/34 in the central florets of the daisy, and 21/34, 34/55, and 55/89 in sunflowers. Evidence of God's flawless creation can be found in all this fine measure and regularity. The flawless creation of plants has been revealed in a verse from the Qur'an, and we are told that this is also important proof for believers. It is He who sends down water from the sky, from which we bring forth growth of every kind, and from that we bring forth the green shoots, and from them we bring forth close-packed seeds, and from the spathes of the date palm, date clusters hanging down, and gardens of grapes and olives and pomegranates, both similar and dissimilar. Look at their fruits as they bear fruit and ripen. There are signs in that for people who believe. Geometrical shapes are by no means limited to triangles, squares, pentagons, or hexagons. These shapes can also come together in various ways and produce new three-dimensional geometrical ones. The cube and the pyramid are the first examples that can be cited. In addition to these, however, there are also such three-dimensional shapes as the tetrahedron, octahedron, dodecahedron, icosahedron, and hexahedron that we may never encounter in our daily lives, and whose names we may never even have heard of. The dodecahedron consists of 12 pentagonal faces, and the icosahedron of 20 triangular ones. Scientists have discovered that these shapes can all mathematically turn into one another, and that this transformation takes place with ratios linked to the golden ratio. Three-dimensional forms that contain the golden ratio are very widespread in microorganisms. Many viruses have an icosahedron shape. The best known of these is the adenovirus. The protein sheath of the adenovirus consists of 252 protein subunits, all regularly set out. The 12 subunits in the corners of the icosahedron are in the shape of pentagonal prisms. Rod-like structures protrude from these corners. The first people to discover that viruses came in shapes containing the golden ratio were Aaron Klug and Donald Casper from Birkbeck College in London in the 1950s. The first virus they established this in was the polio virus. The Rhino 14 virus has the same shape as the polio virus. Why is it that viruses have shapes based on the golden ratio? Shapes that are hard for us even to visualize. Aaron Klug, who discovered these shapes, explains.